Okay, good morning. So today will be almost completely about the persist part of our softwares, and so I'll just give a brief introduction to what this is going to do, and also to the basic statistical questions that all of us have and that are going to be tackled in the persist software. So probably the most frequently occurring question that we are usually faced with is when are two values different. So that's you made an experiment where you have a control sample and you have a sample that was treated, stimulated in whatever way. And so that's probably the most standard question that you want to know. Did now the value for a certain protein, did the expression of a certain protein change upon your stimulus? And so of course, you can make one measurement control, one measurement stimulus, but we all know that's not really good practice. One should make replicates for both of the groups. So for example, you would make here 3 control biological replicates and 3 stimulus biological replicates. And then the question is then the means of these numbers or the medians or whatever measurement of the mean you want to take, are they different between the groups? And obviously, the more replicates you make, the better you can judge if these are different. But then obviously also more replicates take more time, more money, so you don't have the possibility to do infinitely many of these. So then the question is, can we just by measuring the mean of the expression value of the protein in control and stimulus, so just by taking a threshold on the mean, can we say if it's different or not? And probably not, because if you now look at 3 different situations that you have here, so these are 3 different proteins that have the same difference between means between the control and the stimulus group. You would still say that these proteins are not equal in terms of certainty that these are actually different in the 2 samples, because it not only depends on the difference of means between the control and the stimulus group if you're certain that the value is different, but it also depends on the variability that you have within each group, right? So that's actually the main difference between these 3 proteins that have the same difference of mean between the 2 groups. The main difference is that one of them is actually very tight in both of these groups. The orange one here. So there you would be very certain that the expression value between the 2 conditions is very different. But for the other ones, you would not be so sure. So particularly the one with the very high amplitude of within group variability, you would still not be sure, even though you have made already lots of replicates, that these are different, right? So we have to capture this relationship between difference between the means and variability within the groups. And make some mathematical formulation that tells us then if this is significant or not, right? So that's what we do like this. And that's actually going to be the t-test. That we look exactly at this ratio here. So we look at the ratio of this difference here to the amplitude of the within group variations, or you can also look at the square of these, which is then the variance. So it's this ratio here that is going to be relevant. It's the variance between groups, which is nothing else than this difference here squared in the case of 2 groups. The ratio of this to the variance within groups, right? Just calculate the variance in this group, add the variance in this group, and that's basically the denominator. And that's already the test statistic of the t-test. So if this is big, it's good, right? So if this is small, then we're not sure if this is going to be different or not. Right, so that's the t-test. Okay, I don't go into the details how you now calculate the p-value. So basically, the p-values tells you if how likely it is that the null hypothesis is basically true, so that there's no changes. But so that's a straightforward mathematical procedure that's basically built on top of this test statistic there, right? So I won't tell you how this works exactly. but you probably also have seen that already. So that's the way how you would actually measure if a single protein is changing or not changing, right? But on top of that, we have now the problem that we test many hypotheses at the same time. So it's not just one protein that we're looking at, it might be 10,000 proteins that we're looking at simultaneously. And these single p-value approaches, they run then into the problem we called multiple hypothesis problem. And so what this is, you see in this example here. So let's say we have now measured 2 replicate groups and we found 10,000 protein groups in MaxQuant that were quantified. And now we load this into Perseus, this matrix. And now we're going to make 10,000 tests on these 10,000 proteins in the matrix to ask if they are differentially expressed or not, right? So, so the problem that we have now is that we have an increased chance of picking up false positives. And so the best way to see this is suppose now that actually there is no difference between control and treatment. Actually, your treatment, let's say that you didn't actually treat, but these were just, again, n control samples, right? So you should not actually pick up anything as being significant. However, you run into a problem if you now work with a fixed p-value threshold. So because, let's suppose none of these, so as I said, we assume now none of these 10,000 proteins is differentially expressed. But still, you would now, if you work with a p-value threshold of, let's say, 1%, 0.01, you would still call 100 as being significant because like in the simplest assumption, the p-value that you would get from a population where nothing is changing is equally distributed on the interval between 0 and 1, right? So that's a good assumption. Then actually of these 10,000 p-values that you calculated, 100 would be between 0 and 0.01, right? If it's equally, let's say it's not 100% equally distributed. I mean, that might have a certain different shape, but to good approximation, we are getting something around 100 proteins that we would call now as differentially regulated in this setup, right? And you see that that's of course unacceptable. So that's definitely not the result that we want to have. So what do we do now to solve this problem? So there are basically 2 approaches you could take to solve this problem. So one is the so-called family-wise error rate approach, and the other is the false discovery rate. So in the family-wise error rate approach, you basically control the chance of making a single mistake, right? So basically what you control is the probability of making at least one false discovery. And you can already imagine that this is a very, very strict, very conservative approach, which is good on the one hand because you never make mistakes, or you control this one first mistake that you make, basically, right? So everything you say is very, very correct, which is good on first sight, but then, of course, it's not good because you're losing a lot of information, right? So a lot of things that are significant you will just miss with this approach, right? So this is what you do if you calculate the Bonferroni correction to the p-value, which is essentially multiplying the p-value with the number of tests that you were making, right? So then if you, let's say, made 10,000 tests, and usually you would use a threshold of 0.01, then your threshold would become 1 to the power of -6. So you see you would work with very, very strict p-value boundaries. You will lose a lot of information. You will waste a lot of money. So that's why people are not doing this, basically, right? At least not in proteomics. So instead, so the alternative to this is the false discovery rate approach. And so here you're not interested in making no error or estimating the probability of the first error you're going to make, but you say, so I'm going to be happy with making a certain percentage of errors, right? So I'm actually happy if like 1% of my claims are wrong, so that's good enough for me, you could say. Or, I mean, that's of course variable. You don't have to pick 1%. You could also say 1 per mil or something like this, right? So whatever you feel like, it's just, these are standard values that are kind of common in most proteomic studies that you want to have like 1% certainty on the protein level, for example. So here control the proportion of false positive among the set of rejected null hypotheses. So among the set where you claim, okay, this is going to be differentially expressed, you want to have this certain percentage, basically. Yeah. So you have a strongly reduced number of false negatives with this approach compared to the family-wise error rate. And so then we're going ahead with the second one. We're not going to follow up with the first one here. Yeah, so the first one, that's essentially the Bonferroni correction. Then if you want to do if you want to control the false discovery rate, there are still a couple of possibilities. So two best known is the Benjamini-Hochberg correction. And the other way of doing this is with permutation-based methods, right? And so what are these? So Benjamini-Hochberg is actually an adaptation of the Bonferroni correction to be less conservative, but actually still being an upper bound to the FDR to the false positives that you can have in a sample. And as you probably have seen this is a very simple procedure. So if you have calculated your p-values and you assume that these are correct, actually, so that basically all requirements are fulfilled. For example, if you need normality for the p-value to be correct, then that also has to be fulfilled here. So you still need this normality, and so it's essentially just multiplying the p-value with a number which just tells you where you are in a table, basically. So it's kind of an adaptive Bonferroni correction. Take into account where you are in this sorted list of p-values. It's a very simple procedure, very easy to calculate, and it will actually give you an upper bound on the FDR. So it's not trying to estimate the number of false positives, it's an upper bound on the number of false positives that you will have. So it's basically guaranteed. So if the p-values are actually correctly calculated, it's basically guaranteeing a bound on the false positives. So the permutation-based approach works very, very different. So it's actually a bit similar to what we do in proteomics with the target decoy approach, basically. So you basically at first you don't know what your null distribution is, basically, but you can create one by basically doing nonsense calculations or offering nonsense results, basically, to your algorithm, basically, right? And so how do you offer nonsense results in this permutation-based approach? So we know that in proteomic searches, in the target decoy approach, we reverse peptide sequences and we make up basically proteins and peptides that don't exist in nature. And whenever you hit one of these made up proteins or peptides, you know that you made the wrong discovery, basically, right? And so we do something similar here now. So let's say we have now like proteomic expression data set, label-free ratios, labeling doesn't really matter, can be anything. And so we have now 6 control samples and we have 6 treated samples. And so now we want to know out of these which are significantly changing. And we again have, so I draw only 5 proteins here, but these are again 10,000, of course, really. And so then we calculate the p-values of whatever test we chose, so t-test in this case, on this data set as usual. But then in addition to this, we now come up with a number of other data sets where we would expect that nothing should be significant. And so we do this here now by taking the same data as we measured and just scrambling the grouping. So we make up new control and stimulus groups by mixing the members of the old groups. And actually we mix them, so it's actually best to mix them in an even way so that you get, for example, always 3 of the true controls into the new control group and 3 of the stimuli into the new control groups, and the same for the new stimulus group, right? So that it's really even and there really should not be any effect on these groupings, right? And then we do this then for many permutations, basically, right? So there are many ways to sample, like 3 and 3 from here and 3 and 3 from there, and we go over If it's a small number of replicas, you can do this exhaustively. If it's becoming big, then you just subsample 99 times or whatever. So you have now many of these data sets where nothing should be happening, and you just calculate the p-values on these as well, right? And then you have this population of p-values where you offer the ones where you really want to know what it is, and you offer the ones where you know that's not going to be significant. And then, just very similar to the target decoy approach, just by counting, you can now actually estimate the false discovery rate, right? So that's how it works. And so that's also what we're going to prefer of using over the Benjamini-Hochberg method, actually for several reasons. So this has actually many advantages over the Benjamini-Hochberg. So obviously the disadvantage is not as easy to calculate. It's not just some simple formula you apply to the table, but you have to do some calculations in the background. But so some of the many advantages are, so one is, this is not an upper bound, but this is an estimate of the FDR, right? So that might be a matter of taste if you like upper bounds, if you want to be absolutely mathematical sure and things like this. But I can tell you the upper bound is not very tight. So actually we made a couple of studies where we compared both of these methods, and so the upper bound can be easily off by a factor of 10 or even more, or something like this, right? So again, this is more conservative than you really like to be, and you might be wasting a lot of discoveries, or you're not seeing a lot of discoveries because you're using this method, right? You will see more basically on average if you use a permutation-based method. The other big advantage is it doesn't rely on on violating or fulfilling the assumptions that the p-value comes with. So, for example, the t-test comes with the assumption that you have normally distributed data, and that's also true. So, if your data is not normally distributed, then of course your p-value is not correct. You cannot take this as a probability as is, basically, right? But still, you can use it as a number with which you rank your table and with which you go through this permutation procedure, right? So there's nothing wrong with that. So even if you violate your assumptions for your test and you go through this procedure with your p-value, then the FDRs that are coming out of this, they're valid, they're correct, right? No matter what you validate. Actually, you could come up with any crazy score that's in your head and apply it to the permutation-based FDR, and it will be correct. It might be just the case that the score was not a good idea, and you won't find anything, but at least it will not underestimate false positives or something like this, right? So your coverage may suffer if your score is not good, but you won't make false claims, right? So I think this is actually the biggest advantage of the permutation-based approach, that we're not tied to the normality assumption with parametric tests, right? So that's kind of, yeah, very nice to have this, because I mean, to be true, if you look at proteomics data, it's nearly never normally distributed, right? So that would then suggest in the first, I mean, if you look at the statistic textbooks, then it would say you have to use non-parametric tests. However, you will find out if you use non-parametric tests on proteomics data, you will have to make many replicates to get anything significant, right? Because in the non-parametric test you have less assumptions, but that means that you also need much more information, basically, to know what actually the distribution is that you don't assume to be there, right? So this is basically, this is kind of the really nice part of this, that we can use the power of parametric tests and don't make mistakes, right? So the only thing you cannot do is take the p-value literally as a probability, but you can use the FDR estimates on t-tests. Okay, so that's why also in the exercises, what we will do, I mean, in PERSEUS you can do all of these if you want. In the exercises we will do this, because that's also what we do in practice, basically. Okay, so then, so next thing is, so we want to bring, so all of this now, the testing is kind of scale-free. So basically, the testing doesn't really know, and actually that was on purpose. We didn't want this in the game. It doesn't know what is the scale of your changes. So it just looks at how consistent is the change, right? But it's so far, if you only use the test, it doesn't really matter if your change is tenfold or it's just 10% change, right? So as long as you have a good, like a proportional increase or decrease of the within group variance, this is the same. So if you just multiply everything with a factor of 10, your protein ratios, the test results will not change, and also what you get out of the permutation-based FDR will not change, basically, right? But then, so now we did everything to get rid of the scale, but then we want to reintroduce it because it's actually, then one finds it is actually important if a ratio is only like 1% change or if it's like tenfold change, so that must make a difference somehow. And also, so that's why for biological applications you always bring back the scale by using a volcano plot-based approach. So volcano plot is, so obviously it looks like a volcano. And what you see here is actually on the x-axis, this is the effect size. So that's the difference between means, for example, in the two-group test. And this is all on logarithmic data, of course, right? So that's the log ratio fold change here on the x-axis. And then on the y-axis, you plot the p-value. So this is the raw p-value from the t-test, not with this fancy permutation-based thing on top. And you like to plot minus logarithm of the p-value here, so just that it looks nice on scale, basically, right? And so this could be any log with any base, but then so traditionally you like to take base 2 here, because then it's easy to see, oh, here at 1, so if this is 1, it doubled, basically. And this you usually, you put log 10 here for the p-value. So then you see the orders of magnitudes, how the p-values are changing, basically. And then, so from the permutation-based FDR, what you would get now, so far, is this significance level here, right? So the permutation-based FDR would tell us if we cut off the p-value list at this particular value, then we would get exactly the FDR that we were imposing, for example, 1%, right? So then this would be the significant ones here on top. But then, so usually in these volcano plot-based approaches, as I said, you want to bring back the size of the effect into the decision, which means it's not just a straight horizontal line that's going to be the decision boundary. And so there are many ways to do this now. So some people like to put boxes or rectangles or something like this in here. We like to put more smooth curves that somehow follow the distribution a bit better than just boxes of horizontal and vertical lines. And so we really like to use this very old SAM method that's coming from the days of microarrays, where one does some politely said correction to the test statistic, or it's just some, you just change it basically. So you add basically to the test, this is again the test statistic that we saw in the beginning. You have the difference between means in the numerator, and the denominator you have the variance or standard deviation, depending if you square root it or not. And so what is done here, you just add some artificial variance to the data called S0, so that will also pop up as the S0 parameter later in the data analysis. And so this is basically changing the test statistic and the effect of this. So now if you calculate back what does this do to the volcano plot, the decision boundary, is this here. So you don't have a horizontal line anymore, but you have these nice kind of hyperbolas, although they're not hyperbolas. So it's something you can only, so you cannot write it down in closed form, but you have to determine it numerically from the formula. And so this is now going to be your decision boundary. And so what it does is, so if you have a large effect size somewhere here, then a less significant p-value is already enough compared to if you're here where you have a small effect size. So here you would need a larger p-value to call it significant, basically. And that's exactly the thing that we wanted to have for biological application. That so if you say that something with a very small effect size is significant, you need to have a better p-value for that, basically, right? So that's exactly what we want for biological applications. So then, that's basically the way we almost always do the test. So in pull downs, but also in proteome expression samples. So this can also be generalized to ANOVA, NY ANOVA. So it's basically always the same trick that you add artificial variance to the denominator in all of these cases, right? So, right. So that was that to that topic. So then probably next thing you want to do is, so now that you've defined what is significantly changing, you want to know are certain biological processes, pathways, compartments, so any kind of annotation you can get your hands on, is any of these enriched in the significant ones? And for this you use the Fisher exact test, which is basically going through all the terms that you offer from a certain annotation. So, for example, Go compartments or something like this, or in this case, biological processes, and it puts a p-value on if there's enrichment for a certain class, for in this case fatty acid metabolism. If this is there are more of these than expected in the range of significant proteins, right? So we will see that in the exercise as well, how that exactly works. So maybe let's go through that quickly. So here you see the result table, but as I said, we will do this in the exercises. So you can also do enrichment analysis in a threshold-free approach. So threshold-free means, so here you had a threshold because you had to define what is significant and what not, basically, but you can also do it without this definition, basically. So you may get out a continuous parameter telling you how significant the result is, or you can also do it on the ratios themselves between samples. So then the question would be, so given a certain distribution, so in this case actually of protein abundances, is a certain class of proteins enriched at high values of this distribution? Like, for example, here, so trivial example, this is the concentration of all proteins, and the green ones are the ribosomal proteins, and then we need a test telling us if these are enriched at high values. Of course, in this case, we don't need a test. Our eyes are enough, but of course, there are not so clear cases where you need a test. And also, you want to do this automatically on many, many categories, and make then p-value decision, and also do the multiple hypothesis correction, importantly, of course, also in this case, because you're going to test many of these categories. So that's also there, will be covered in the exercises. So there are also several methods of these. So one of them we came up with ourselves, and we mostly came up with it because it's generalizable to multiple dimensional tests. So if you have multi-omics data, this is also generalizable to testing if this is, for example, enriched in certain regions of the transcriptomic proteomic space, basically. Well, we will come to that later. So then, of course, in PERSEUS, you have all the bread and butter tools that you need for doing any kind of omics analysis. So you have hierarchical clustering, which probably all of you know. So I won't go into details of that. Will also be covered in the exercises. You have principal component analysis, which is essentially a dimensional reduction technique. So it basically rotates your given data to a particularly interesting space that covers most of the variance of your data. So that's what happened here. But of course, the rotational projection is not coming from two-dimensional data, but again from our 10,000 dimensional data into 2 or 3 interesting dimensions. And that will also be covered in the data. So then briefly, what we will see about cross-omics data analysis in the exercises. So we saw already yesterday that you could also process the NGS data nowadays with proteomics and get the transcript expression right away. And then there are tools to map proteome and transcriptome data to each other, or in this case also ribosomal profiling data. And you can then, as a first instance, like the most trivial thing you could do, just compare these in scatter plots to each other. So we saw that already. Will also be done in the exercises. And then you could basically a bit manually fish for outliers in these plots and see, okay, why is something much higher in the proteome than it was in the transcriptome or something like this. So you could this basically do one by one, so one protein transcript pair by protein transcript pair. But then we also have tests that will point you at interesting pathways that are showing consistent behavior in 2 or more omics dimensions. And so this is basically the straightforward generalization of this 1D annotation enrichment that we already saw, to multiple dimensions. So for example, 2 dimensions here. And for example, you might have measured same samples in proteome and transcriptome, and then you build ratios between 2 conditions. And so then this method would actually now calculate a score for each category that you're using. So for each pathway, biological process, you name it, basically, a compartment, it would give you a 2-dimensional score. And so this is consisting of a proteome dimension and a transcriptome dimension in this case. And if this 2-dimensional score is in different regions of this plot, it has different consequences. So for example, if you are somewhere here with your score, with some whatever pathway, that means this pathway is actually showing same behavior on the transcriptome and proteome, right? So in both it's going up, right? And so if it's here, in both it's going down. If it would be here, so then you have more interesting cases. So if you end up with your score here, on close to this axis, that would mean that there's actually no consistent behavior in the transcriptome of the members of this biological pathway, whatever it is. But on the proteome there is, right? So that means you have to have post-transcriptional regulation to get basically the numbers of proteins into the correct numbers that you need for this process to function, basically, right? So everything that ends up here means you have post-transcriptional regulation happening, be it protein degradation, RNA degradation or inhibition, or so something in between has happened, right? And then if you can imagine now, if you don't only take proteome and transcriptome but also ribosomal profiling, you can actually narrow down where exactly this post-transcriptional regulation is happening, basically, right? So here you just see an example of haploid versus diploid yeast where proteome and transcriptome are measured, and now this plot is basically filled by all kinds of Go terms and pathways. Right? So then we also have machine learning, supervised learning in Perseus, but actually for a completely different purpose than you have heard in the previous talk. So this is actually for classification of expression profiles. So a typical case would be patient studies where from each individual you have any kind of omics data actually would work with it. So let's say proteomics plasma samples, and now you don't use a clustering algorithm or PCA to find out in an unsupervised way what is happening in the data, but now you use an algorithm where you tell the algorithm, okay, these are coming from healthy individuals, these are coming from individuals with a certain disease, or usually it's subclassification of diseases, or any of these can be any kind of questions related to individuals that the probes were taken from, right? And then we use the trained predictor on new examples, basically to find out if this person is having this condition or not, basically, right? And so then this is, of course, used in many ways. So, of course, one should use tools like cross-validation to find a good predictor and to find good parameters of the predictor. So that will also be done in the exercises. And one thing that it also gives you is, so these methods can tell, this is basically complementary to t-test kind of approaches. It can tell you which of the features, and so in this case, which of the proteins actually important to make this decision. So the machine learning algorithms themselves can also tell this. So for example, if you use a support vector machine, especially with the linear kernel, then it is actually very easy to extract from that what were actually the features that were used to make this, or which features have the biggest weight to make the decision if you're healthy or sick, basically, right? And so that's a completely complementary way to testing with multi-hypothesis correction to find signatures, predictive signatures for making a decision. Also covered in the exercise. And so in this context, so we mostly use support vector machine. So it's not, so there are actually many machine learning algorithms implemented there, but so since this has a quite different dimensionality from compared to the deep learning approaches that you have been seeing, this is actually an area where support vector machines are performing very well. So this is, you are here in the situation where the dimension of your space is very, very high, and the number of examples is very, very low, right? The dimension is the number of proteins, so let's say again 10,000. The number of examples is the number of participants in the study, and that's always very limited because it's a cost factor, and you're always very lucky if this reaches 100, so it's often actually below. So it's a two-digit number often. So it's a very sparse space, and that's a space where support vector machines are working very well. Yeah, that's a support vector machine. So I think we're running out of time. So here, that's what the software looked like. You will see that for sure very, very often today. So I won't go into the details much. So the data structure, so the software has one data structure, which is the matrix that is flowing through the workflow. So it's a workflow-based data analysis tool, and through the workflow is flowing this data structure called matrix, and it's actually an augmented matrix because it has a couple of additional added features. So that would be here the matrix of expression values. So for example, LFQ intensities would be here, samples would be in the columns, protein groups would be in the rows. But then you can store a lot of additional information, so annotation to this matrix. So for example, here you would store information about your samples, which could be simple things like what is the grouping of controls and stimuli and things like this. But it could also, if these are patient-derived samples, this could then also be patient record-derived information. So all kinds of things that you then later can cross-correlate with the expression values, basically. And then here you have annotation on the proteins, so pathway membership, Go, and this can come in like several flavors, so this can be categorical annotation, numerical annotation, or just text and text annotation, basically. If you went to the plugin programming bootcamp, you know already that Perseus has a plugin architecture, so it's not a monolithic software with a fixed set of commands, but you can program your own commands and add them to the software, so that are these so-called plugins. Yeah, so people who were at the workshop know how that works. And so there's also a plugin store where basically you could share plugins with other people. And these plugins, so you might think, since this is written in C#, you might think you have to write the plugins in C#, which not everybody might be familiar with. Although, let you be said, this is very similar to Java, so Java is probably more common and more people know that. So in the way of thinking, it's the same as Java, but you exchange some words basically. But you don't have to use C# because we have this extension where you can program plugins in R and Python. And so that the prime application is probably not even programming yourself, but just using stuff that is already written in R and Python, right? So things like, as we saw, we use DSeq2 for doing differential expression on transcriptome data, and we can just integrate it here through this R and Python plugin infrastructure. So this can just become a command within the Perseus workflow, basically. Yeah, so we also have support for networks. So we will see that in multiple examples. So for example, if you have a large pull-down experiment, you can automatically create the interaction network from there. So I think that's it for the general overview. So you will see all of this in the exercises. So let me just give you a few important web pages. So we have prepared annotation files from UniProt. So basically, projecting it down to single species, basically, and putting it in a tabular format that we can read. So if you work with this new species, you can always download the annotation from the server. And before you're asking, we just updated the annotation, so it's really fresh. So it's like 2 weeks old. It's new annotation from UniProt on this server. So many of the plugins are open source and are in this GitHub repository here, so you can see the source code. So the way you should deal with problems that you encounter, so especially if these problems are reproducible, and if these problems are happening in the latest version, so these were two very important things. So it has to be reproducible, and it has to occur in the latest version. Then I highly encourage you to report this problem in this bug reporting system here, UTrack. So you just go there, you have to sign up, and then please say specifically what a developer has to do to reproduce this problem, and we will do our best to fix this, right? So if you say, oh, a problem, something is crashing, so then we cannot do anything, right? So you have to say, please load this file, do this and this and this, and this bad thing will happen. And so if you tell us that, then we can very quickly also fix the problem, basically, right? And so what we also have is a Google group, so it's very similar to what we have for Max Planck. It's also quite populated, I think 1,500 or something users are there. And so there, just by searching there, you probably find the answers to most of your problems already, basically. Okay, and so we are over time, so I don't know if we should take questions now, or maybe only very important ones. But I mean, the whole day will be about this, right? So there will be plenty of opportunity to ask questions.